Hello everyone, so this is our group project Serial Multiplier and we are from group 4. So we are consists of 3 members, which is Wang Yishan, Lai Yihan and also Dev. So we designed a digital system called Serial Multiplier to multiply to 8 bits binary number. So we use a FSM+D approach, which consists of CU and DU, and also we're using a top-down approach that we break every system of our every unit of our system into smaller parts. So we are using the ADA playground as our ADA tools to design, simulate and verify the system. So this is our overall design that we first read the X and Y, and also then we initialize the register total and counter into 0 and 8, and then inside the while loop we are doing the multiplication by adding and also shifting of the operation. Then this is the table that showing the step for the multiplication and shifting process. So we can see we are start to multiply from the MSB of y, and then go through from stage 1 to X stage, and then the final result will be out in the last stage, which is the X stage. So this flowchart is clearly show how we control our flow, how the register is being loaded, and then how the decision making during the changes of the stage. So this is the ASM chart of our control unit. Then we can clearly show that we have a total of 6 stages, and then each stages is clearly show that which control signal will be activated and how the transition of the stages itself. Then this is the RTL ASM chart of our system. So in this chart we can see how the register is being loaded, and then how is the decision making for each stages, and to do the shifting and also the addition. Next is the RTLCS table. So in stage 0 we can see that there are no control signal being activated. In the stage 1 there are 2 control signals activated, which is load X and Y, and in the stage 2 no control signal activated. Then we go to stage 3, load shift total is activated and decrement, and also the marks enable. In the stage 4, load shift total, decrement, enable marks, and also the selector. In the last stage only load total is being activated. Then on the right hand side we can see that the FBD of our CU and DU, we can see the output, some of the output of the DU unit is used to control our next state logic in the CU, and also the output of the CU unit will use to control the DU.
Hi, good morning everyone. My name is Wang Yishan and I'm going to continue for the control unit part. So here is the full body diagram and the Verilog code. So we have the CU, which we have 5 inputs and 8 outputs listed here, and we have been using the 3 segment coding style, which we have the state register, the next state logic, and the upper logic coded. So the upper logic coded is in the mode style to control the data path unit. So here is the test bench for the control unit, and here is the simulation result. So we have the start here to control the system to enter through the second stage, which we have the load for the multiplication and the multiplier. So we have the y equal to 1 to check the least significant bit of the y. If it is 1, we'll be entering the stage 3. If it is 0, we'll be entering to stage 4 from the stage 2. Then it will different in the selector where 0 will be added, 0 and 1 will control what value will be added to the partial product. And then when the count is equal to 0, it will continue to stage 2 to stage 5, which we output and load the total multiplier result. So here is the data path unit. So this is the full body diagram, which we have 2 registers to contain the data of multiplier and multiplication, and the mask and selector to control the addition, and the comparator to check the y is least significant bit is equal to 1, and the counter. So this is the register total to contain all the final value and the shift left register for the shifting. So here is the counter module we will be using, and the adder module and the shift left register module. So this is the full whiteboard code for the data path unit with a stats bench here. Then this is the simulation result. So this test bench is used to verify the operation of the 8-bit serial multiplier by performing the multiplication of 10 multiplied by 50. The reset signal is initialized in the data path by clearing the register and setting the counter. Then we have the multiplication 10 and 50 loaded with the load X and load Y. The multiplication process then run for the 8 clock cycle here, which each cycle processing one bit of the multiplier. So the y equal to 1 signals check whether the current multiplier LSB is 1, or the selected signal controls whether the multiplicand added is 0 or a partial product. So at the same time the partial product is shifted, the counter is decremented here. So it will be decrement by 8 times total to 8 clock cycles. So the final result will be stored in the register total and the M total. So this is our result, and thank you. We'll be moving forward to the next part.
Good day. My name is Dev Verma, and I'm going to present on further topic control unit and data part unit. So, we combine both the CU and DU together. So, as we can see in the diagram, that the CU, the input to it is start, reset, and clock. The output is load X, load Y, and similarly other output lines like selection line. And the same output of CU is going as the input to the DU. So as you can see, SEL, DEC, LDX, LDY, they all go as an input to DU along with the parameters like A and B input, which we are multiplying. So after the calculation is done, it comes as T total, and the done flag becomes 1. So on done flag becomes 1, we get to know that the result has been confirmed. So taking to the Verilog code, it's simple, like CU we instantiate, and the output of CU goes as the input to the DU. So as you can see, LDX is an input to DU, but it was an output to the control unit. Now talking about the test bench code we have designed. So first we have given the reset signal, then A equal to 5, B equal to 6. So as we can see, like A equal to 5, B equal to 6, we should give us 30. So before doing that, we do start equal to 1, we start, so FSM gets started with that, and we wait. So let's see the waveform. Yeah, so in the waveform, as we can see, first we give the reset signal. The basic purpose of reset signal is to like put all the default values like 0, so that nothing should be like X on the simulation screen. So with reset, everything gets to the default or the set values, reset values. Now when we want to start multiply anything, so before that we have to give a start pulse. So start impulse we have given, and once the clock signal gets hit, so as we can see, the current state, it has started to increment 1, 2, 4, and 2. And on similar line, the calculations of A and B like 5 and 6 has started to happen. Now, like as you can see, first come 5, 10, 15, and at the end we get the result as 30, as you can see. And at the same time, at the top we see the done signal as getting from 0 to 1. That means the result has been confirmed 30 and we can use it. On similar lines, we have also done for multiplication of 10 and 30. Same result, we are getting 300 and done flag as 1. Same for 10 and 5, 50, done flag as 1. And 5 and 5, 25, we get the done flag as 1. And intermediate operations are also, so what is the result is shown in the T total. So now the conclusion is we have produced correct result for all the test cases including edge cases, and the design is simple. As you can see, we have segregated CU and DU. However, it might be slower due to multiple clock cycle as things are segregated, but it has successfully been implemented. There are some limitations like it's fixed bit, no sign support. Future improvement, yes, we can build parallel architecture. As of now, it's just normal. So parallel architecture for faster performance. Thank you.